The first slide is talking about why we need spanning tree. Ethernet frames don't have a TTL value, so they can move between switches eternally. Because of that, we can face with broadcast storms. For example, let's say that PC1 sends broadcast to our network. Because of that's a broadcast packet, our switch takes the packet and flutes it from its all ports. This traffic comes to the switch 2. Switch 2 also takes the packet and flutes it from here. And switch 3 also takes this packet, and because of that's a broadcast packet, this is gonna flute this also. And another flute will come also on that way. And as you can see that we can face with the broadcast storms too in a topology like that, because Ethernet frames don't have a time to leave value. The another thing that why we need spanning tree, the another answer to this question is we can face with the unicast duplicate frames. For example, PC1 tries to send a frame to PC2. Switch 1 knows that PC1 is on its fast Ethernet 01 port, but switch 1 has no idea about PC2. Because of that, switch 1 will flute the traffic out from its other ports. The traffic will go in that way and will go in this way also. After packet frame will come to the switch 2, and switch 2 also will send the packet to switch 3, and switch 3 will send the packet to PC2. But from here, we have the same frame to coming to switch 3. Switch 3 will also send this packet frame to PC2. So we are going to face with the unicast duplicate frames on the switch. PC2. So what spanning tree protocol is? That's building a logical loop-free topology for Ethernet networks by blocking some of ports. Spanning tree protocol allows a network design to include redundant links to provide automatic backup paths if an active link fails also. Let's think that we are sending a broadcast again from PC1. Switch 1 takes the traffic and flutes it from this port, and also it's going to be fluted from this port. But because of this port is blocked by spanning tree, the traffic will not pass through this way, and it won't go to the switch 3 from this way. So only the green traffic will come to the switch 3 and will affect the PC2. We have three port roles in spanning tree. The first one is the root port. Closest port to the root bridge is root port. But please pay attention that closest to the root bridge in terms of path cost is the root bridge, which I'm going to tell you about this. What is path cost? And we have also designated ports, which mean the ports that are going ahead to forwarding the traffic. And we have non-designated port, which means a blocked port. As you can see that in here, fast Ethernet 01 is blocked, so that role is non-designated. Fast Ethernet 0, 2, 3, and 4 are designated ports, which continue to forward the traffic. And these are the root ports, because of they are closest to the root bridge in terms of path cost value. So let's take a look to how we can elect the root bridge. To elect the root bridge in a red network, we need to define the lowest bridge ID. To find the bridge ID, we are using priority value and MAC address. And we are using an extended system ID to support VLAN for STP. But in most cases, we are not going to use this value to calculate the bridge ID. Please keep in mind that default priority value for switch is this one, and bridges use special data frames called BPDU to exchange information about bridge IDs and route path costs. So let's take a look to this example and let's try to determine the root bridge. The first thing we need to check is priority value. As you can see that in the figure, priority values are same for switches. So second thing we need to check is MAC address. Because we need to find the lowest bridge ID, we need to find the lowest MAC address. The switch which has the lowest MAC address will be our root bridge in this scenario. If you check here, this MAC address is 0017. This is 0024, which is bigger, so I eliminated this. This is beginning with 5 and I eliminate this also. And this is beginning with 001, this is 7, but this is A. A is coming after 9 at the hexadecimal format. So I'm eliminating this, and because of this switch has the lowest MAC address, it's the root bridge. So now let's take a look to the spanning tree path cost. Spanning tree cost value is inversely proportional to the associated bandwidth of the path, and therefore a path with a low cost value is more preferable than a path with a high cost value. As you can determine from this chart too, a higher link speed shows us a lower cost path value. Okay, as you can see that in the picture, in STP, I'm taking a 10 gigabit per second link as a cost value of 1. And I'm taking a 1 giga also a cost value of 1. But I'm taking a 10 megabit per second, which is a slower path, has a higher cost value, as you can see that. We have a reverse logic in here. So if we check the path 1, the cost of path 1 is, according to the revised IEEE specifications, these values were revised. So we are accepting this one now. So let's take a look to the cost of path 1. Path 1 has 2 fast Ethernet links. So its cost value is 19. Let's take a look to the path 2. We have 2 fast Ethernet links together, and we have another 2 fast Ethernet links together, which means we have cost value of 19 for both, and the whole cost value of path 2 is 38. So path 1 is preferred over path 2. So we have a question in here: which switch is the root, and determine the port roles. The question is saying me that because of the priorities are same, I need to check the lowest MAC address. And lowest MAC address is on switch 3. 0011 80, but the third thing is 3 in here, which is the lowest, and that shows us this is our root bridge. As I told you that switch 3 is the lowest bridge, I couldn't speak. Switch 3 is the root bridge because it has the lowest MAC and priority is equal. And let's take a look to the port rows. This is my root bridge. The closest port to the root bridge from a path cost value point of view will be the root port for each switch. For example, let's check the switch 1. Here we have a fast Ethernet path to get here, which means my cost is just 19. But if I want to get from this way, I need to pass fast gigaway, gigaway, and gigafast way, which means higher cost value for me, and this is the root port for switch 1. And for switch 4, here, this is the root port. And for switch 2, this is the root port. Because this is a giga and fast way, but here, this is a giga and fast way, but this path is fast and fast path. So giga is faster, so this is our root port. Okay, we determined our root ports. Please keep in mind that for each segment, I should have a designated port. And please keep in mind this too. My root bridge ports are always in the designated mode. So I'm going to my root switch and writing the port rows as designated. Okay. I determined this one. And what I told you is for each segment, for each link between switches, we should have a designated port. So because of this is root port in here, this is going to be the designated port too. Okay. Here is okay too. Now we just need to determine these two ports. Now I'm comparing switch 1 and switch 2. I'm going to choose one of these ports as designated, and one of these ports will be a non-designated, which means blocked port. To choose where I'm going to block, I'm comparing these two devices' priority, and I see that they are same. And secondly, I'm comparing their MAC addresses. The lowest MAC address will not be blocked. As you can see that in the picture, switch 1 has lower MAC address. Because of that, Fast Ethernet 02 of switch 1 will be designated port, and this port of the switch 2, GIG 02, will be non-designated and blocked port.